In this video, we're going to look at some triple integrals. We're going to practice some triple integrals. So let's take a look at this. This says evaluate the following integral where E is the volume under the plane x equal 12 and above the paraboloid x equal 3y squared plus 3z squared. So we can see from the form of this paraboloid opens along the x-axis. So we can sketch it. It's going to look something like this. And also the plane x equal 12. So I'll just put a 12 right, so you can imagine there being like a plane right there. So it's the volume above the paraboloid and under the plane. So it'll be the volume inside the paraboloid, basically up to x equal 12. And so once again, you can imagine yourself standing within the volume. And if you're in the positive x direction, so this one's going to be pretty natural to integrate over x first. So again, imagine yourself standing in the volume in the positive x direction. So your feet are on the paraboloid and your head is kind of up pointing towards the plane. So again, the paraboloid is x equal 3y squared plus 3z squared. And then the plane is up here, x equal 12. And so we want to see the intersection of those two. And so that's going to, so to find the intersection, of course, set those equal to each other. And so put this into here, basically, since this is equal to x and this is equal to x, we can set those equal to each other. And then divide by 3. If we divide by 3, we'll get 4 equal y squared plus z squared. So I'll write it the opposite way. And divide by 3, that'll equal to 4. Let me write that as 2 squared. So that's going to kind of give us the domain when we do the last two integrals. So once again, you can see that this is a circle of radius 2. And so let's set up our integral. Once again, we have x times y is our integrand. And like I said, it looks like we want to do x first. So we'll put dx here. And then maybe dy, dz. And so again, we're starting, your feet are starting at x equal 3y squared plus 3z squared. And again, your head is pointing towards x equal 12. And then again, the last two integrals will be the projected area back here, and there'll be a circle of radius 2. So this is going to be a circle radius equal 2. So that means what this is going to end up being, when we do our polar coordinates, we're going to have y equal r cos theta and z equal r sine theta. And of course, y squared plus z squared will equal r squared when we do the polar coordinates. So those are going to kind of be our polar coordinates when we change. And so then over here, let's go to the next step. So once again, put our values in. Now what we can do here, we know that x will just be x, so just leave that there. And then y will be r cos theta. And because we're converting to polar, remember, you always have to put that r in. Dx, dr, d theta. And again, notice this lower bound here. We could factor out this 3. So this would be 3 times y squared plus z squared. Three times y squared plus z squared. But remember, that's going to be r squared. That's going to be the lower bound. The upper bound, of course, will still be x equal 12 because there's no variables in there to convert. Again, remember the last two integrals are going to be a circle of radius 2. So it's going to be r equals 0, r equal 2, theta equals 0, theta equals 2 pi. So again, decide what the most natural direction is. The most natural direction is going to be x first. Imagine standing in the positive x direction. Your feet are on the paraboloid x equals 3y squared plus 3z squared. Your head is pointing towards x equal 12. And then, so once you finish x, you have to think of, okay, what are the values of y and z over which I want to integrate? So you have to take the intersection of the plane and the paraboloid, and you end up getting a circle of radius 2. And so you end up, the last two integrals will be a circle of radius 2. And when you, since it's a circle, always convert to polar. So polar will be y equal r cos theta, z r sine theta, and then x squared plus z squared is r squared. And then go ahead and make your substitution, x equal 3r squared, because x squared plus z squared is r squared. And then the upper bound just stays x equal 12. And of course, substitute for y. Y was r cos theta. And then always put in the r. Remember, whenever you convert to polar, always have to have the r in. Then over the circle, r equals 0 to 2, theta equals 0 to 2 pi. Let's take a look at this example. It says evaluate the integral x plus y plus z, where E is the volume bounded by the plane z equals 16, and the parabolic cylinder z equal y squared. So let's take a look at this. So obviously this looks like a parabola, like a two-dimensional parabola, z equal y squared, like that. But because we're in 3 dimensions, though, there should be an X somewhere. But there's no X. So that means we're going to have one of these parabolas for every value of X. So you can kind of just keep repeating that all along the X-axis. So you'll have like another parabola, maybe something like this. And I'm not drawing this very well. Actually, not drawing this very well at all. Let me put this on another piece of paper, see if I can do this a little bit better. That's not good. That back like this and see if I can make this look a little bit better. Still doesn't look great, but hopefully you kind of get the idea. So it's going to look sort of something, like this. It'll sort of look something like this. And so that's going to be our z equal y squared. This is y, z, x. And we also have the plane z equals 16. And so once again, just imagine yourself standing in the volume. So the z equals 16 gives it like a top, so to speak, or a roof over here. And imagine yourself standing in that volume. And so your feet are going to be like down here on the parabolic cylinder, I should call this, on the parabolic cylinder. And your head is going to be pointing towards the roof, v equals 16. So we're going to need the intersection of those two. And so when we put z equals 16 in here and take the square root of both sides, we get y equal plus or minus 4. And I realize now we needed one more bound in our problem. We needed the bound on x. So let's make x go from -4 to 4. So we have y going from -4 to 4. And let's say our bounds on x are -4 to 4. Now let's set up our integral. Now, first of all, notice then what this intersection is. It's just y equal plus or minus 4. And we've also set our range on x was plus or minus 4. So we'll end up with a picture. Something like this. So that's going to be like the domain in the YZ plane. Excuse me. Sorry. This should be X and Y. Sorry about that. So again, we're going to integrate over Z first. And so let's make this X plus Y plus Z. And we'll do from Z equal Y squared to Z equals 16. And then X will go from -4 to 4. And Y will go from -4 to 4. And then that'll be dz dx dy. So once again, we wanted the volume bounded by the plane z equals 16 and the parabolic cylinder z equal y squared. So go from there to z equals 16. And like I said, I forgot to put in this bound. So x will be from -4 to 4. And so when you intersect this plane z equals 16 and this z equal y squared, put 16 in here, we get y equal ±4. We take the square root of both sides. And so y varies from 1 to 4. X was given as varying, from -4 to 4. X was varying from -4 to 4. So then put those bounds in. And we're done. This again, we're just setting these up. Take a look at this problem. We want to evaluate this integral, and where E is the volume within the cylinder, above this plane and below this plane. Again, we're going to set up only. And once again, notice we have a circle, and the circle is y squared plus z squared is 1, so it's a circle radius 1. But there's no x in here, yet we're in 3 dimensions. That means we're going to have one of these circles for every value of x. So that means it'll end up continuing down here. And you'll get sort of something like this. You could probably draw this much better than I can. And then also, there's this plane, x plus y plus z is 4. And so you can see that's going to be, maybe something, I don't know, like up here. Let's say this is 4, 4, and there's a 4 in here. So it's going to sort of cut through here somehow. We don't really need to know how to draw it, but it's going to sort of cut all the way through the lower part of the cylinder. Then the upper one is x plus y plus z is 12. So it's going to kind of come down up here somewhere. And once again, we don't really need to know much of the details. But so once again, it looks like it's going to be natural to integrate in the x direction first. And so, once again, imagine yourself standing in the positive x direction. Your head is going to be pointed this way. Your feet are going to be this way. And so the integral is going to be y squared plus z squared as given. And then, like I said, if we start with x first, the lower plane is going to be here. So that's going to be the plane x equal 4 minus y minus z. And then the upper plane up here somewhere is going to be x equal 12 minus y minus z. So our lower bound is going to be x equal 12. Excuse me, x equal 4 minus y minus z. X equal 12 minus y minus z will be the upper bound. And then notice it's within this cylinder. So the domain for the last two integrals is going to be the circle of radius 1, which is going to be y squared plus z squared is 1. And then when we convert the polar for the last two integrals, it'll be y equal r cos theta, z equal r sine theta. And again, over here, this will be circle of radius 1. And so let's fill these in. And of course, here we can put in now, of course, the other thing for polar, we have y squared plus z squared is going to be r squared. So in here, we're going to have the square root of r squared. And of course, you always remember, actually, this should have been dx, dy, dz over here. Then you're going to have r dx over here. And then we're going to, for the last two, we're going to do polar dr d theta. And so here for x, the lower bound was x equal 4 minus y minus z. But when we switch to polar, that's going to be r cos theta, r sine theta. Same thing on the upper bound, x equal 12 minus r cos theta minus r sine theta. And then the last two bounds will be the circle of radius 1. And so it's going to be r equals 0, r equal 1, theta equals 0, theta equal 2 pi. So let's take a look at this integral. let's say we have an x squared plus 2y plus z squared dv. So let's take a look at this integral. And where E is the volume in the first octant that contains the point that contains the point 400,060,003. I probably sort of should have said here this is going to be like a plane. And let me just show you what I mean here. This is going to be a plane. So it's going to be like the volume in the first octant that is bounded by the plane that contained these points. So I should have had a little bit more description there. So it has the point 400, the point 060, and the point 003. Remember when you were doing planes, we had something like this. So once the volume within that region in the first octant, so something like this. And again, you remember, if you wanted to write the equation for the plane, this plane equation could be made up by making x over 4 plus y over 6 plus z equal 3 equals 1. And then you can actually find the common denominator. So if you multiply by 12, that'll kind of get rid of everything. Multiply by 12, get rid of the denominator. So if we multiply this by 12, we'll get 3x. And over here, we'll get 2y. Over here, we'll get 4z equal 12. Then finally, let's say we integrate in the z direction first. We'll solve for z here. And that'll end up being z equals 12 minus 3x minus 2y and divide by 4. So finally, z will be equal to 3 minus 3/4 x minus y over 2. So I made that picture just a little bit neater. So make this here. Now we determined that z was equal to 3 minus 3/4 x minus y over 2. And so this is going to be your domain when you do x and y. Once again, imagine yourself standing inside this region here. Then your lower bound is going to be z equals 0 because you're standing on the xy plane. Your upper bound, where your head is sort of pointing towards, 3 minus 3/4 x minus y over 2. And I'm just going to write down, remember what our integrand was over here. X squared plus 2y plus z squared and then we're going to need our domain in the xy plane. And so it's over here, it shows x at 4, y is at 6. Yeah, something like that. And so it looks like that's going to be, obviously the y-intercept is 6. And then looks like we're going down 6 and over 4. So 6/4 or 3/2 is going to be the slope. And the y-intercept is 6. So that our line is going to be that equation there. So again, we did our first bound with z. We went from z equals 0 up to the roof here. Z equal 3 minus 3/4 x minus 2. Then we do that one, we focus on the xy plane and this region down here. And now, once again, if you do the y direction first, put arrows in the positive y direction. And that's going to be y equals 0, y equal minus 3/2, x plus 6. And then x equals 0 to x equal 4. And that's your integral. And of course, dz, dy, dx. So let's take a look at this one. It says evaluate this integral, where E is the volume bounded by the paraboloids y equal 2x squared plus 2z squared and y equal 12 minus x squared minus z squared. So let's take a look at this. So again, the first paraboloid, would go out something like this. That would be our y equal 2x squared plus 2z squared. And then the other one, let me get rid of this. Let me move this out a little bit. It's a little bit messy, but again, these don't have to be great, just need to give an idea of what they look like. So you have 12. So this is going to be 12 minus z squared minus x squared. So it's going to be a parabola going in the other direction, starting at 12. So it's going to look something like this. So this one here will be y equal 12 minus x squared minus z squared. And so obviously they're going to open up along the y-axis, so we want to do y first. And let's find the intersection. So we just want to set this equal to this. And then bring these over here. And divide by 3. And something like this. So obviously this is a circle. Of radius 2. And so let's set up the integral. And once again, imagine yourself standing inside the volume in the positive y direction. Your feet are going to start at this paraboloid and end at this one. Like this. And then the last two bounds on the XZ plane is just going to be a circle of radius 2. So just have like a circle here, radius 2 on X and Z, like this. So for the moment, we're just going to write that down. So this is going to be x squared plus z squared to the 4th minus square root of x squared plus z squared dv. And we know the last two is going to be a circle of radius 2. But we're going to change the polar since we have a circle here. So again, we put the final integral in. We'll have y equal 2 times x squared plus z squared, but that's r squared, right? 2r squared. The upper bound is 12 minus x squared plus z squared. That's r squared. And then for the circle radius 2, r equals 0, r equal 2, theta equals 0, theta equal 2 pi. And then in our integrand, we're going to put r squared here. Over here, we're going to put the square root of r squared. And that'll be dy. We need an extra r in there, don't we, for r? Since we're converting to polar, always remember put that extra r. Then dr d theta. Now notice we could probably clean this up a little bit more. If you wanted to, you could maybe make one final step here. And oh, by the way, this upper bound here should have been a 2. And so r equals 0, r equal 2, theta equals 0, theta equal 2 pi. And then now notice this is going to be r to the 8th, but it's going to be times r, so it's going to be r to the 9th. And then square root of this is going to give us r to the first power, but that'll be times r, so it'll be r squared. And then dy, dr, d theta. So like the other examples, always find the intersection of the two surfaces you're dealing with, and that usually will give you the domain.